This photo shows about 26 rolls of paper piled together. The rolls are different sizes. Figure 2.1. When you have large amounts of data, you will need to organize it in a way that makes sense. These ballots from an election are rolled together with similar ballots to keep them organized. Credit, modification of work, Helmand Province, Afghanistan, Aug. 21, 2009. Voting ballots organized and arranged for counting by Afghan presidential election workers at a local school in the Nawa district. By U.S. Marine Corps. Photo by staff SGT. William Greason / Wikimedia Commons, public domain. Chapter objectives. By the end of this chapter, the student should be able to display data graphically and interpret graphs, stem plots, histograms, and box plots. Recognize, describe, and calculate the measures of location of data, quartiles and percentiles. Recognize, describe, and calculate the measures of the center of data, mean, median, and mode. Recognize, describe, and calculate the measures of the spread of data, variance, standard deviation, and range. Once you have collected data, what will you do with it? Data can be described and presented in many different formats. For example, suppose you are interested in buying a house in a particular area. You may have no clue about the house prices, so you might ask your real estate agent to give you a sample data set of prices. Looking at all the prices in the sample often is overwhelming. A better way might be to look at the median price and the variation of prices. The median and variation are just two ways that you will learn to describe data. Your agent might also provide you with a graph of the data. In this chapter, you will study numerical and graphical ways to describe and display your data. This area of statistics is called descriptive statistics. You will learn how to calculate and, even more importantly, how to interpret these measurements and graphs. Statistical graph is a tool that helps you learn about the shape or distribution of a sample or a population. A graph can be a more effective way of presenting data than a mass of numbers, because we can see where data clusters and where there are only a few data values. Newspapers and the internet use graphs to show trends and to enable readers to compare facts and figures quickly. Statisticians often graph data first to get a picture of the data, then more formal tools may be applied. Some of the types of graphs that are used to summarize and organize data are the dot plot, the bar graph, the histogram, the stem and leaf plot, the frequency polygon, a type of broken line graph, the pie chart, and the box plot. In this chapter, we will briefly look at stem and leaf plots, line graphs, and bar graphs, as well as frequency polygons and time series graphs. Note: this book contains instructions for constructing a histogram and a box plot for the T83 Plus and T84 calculators. The Texas Instruments T website provides additional instructions for using these calculators. One simple graph, the stem and leaf graph or stem plot, comes from the field of exploratory data analysis. It is a good choice when the data sets are small. To create the plot, divide each observation of data into a stem and a leaf. The leaf consists of a final significant digit. For example, 23 has stem 2 and leaf 3. The number 432 has stem 43 and leaf 2. Likewise, the number 5432 has stem 543 and leaf 2. The decimal 9.3 has stem 9 and leaf 3. Write the stems in a vertical line from smallest to largest. Draw a vertical line to the right of the stems. Then write the leaves in increasing order next to their corresponding stem. Example 2.1. For Professor Dean's spring pre-calculus class, scores for the first exam were as follows: smallest to largest. 33, 42, 49, 49, 53, 55, 55, 61, 63, 67, 68, 68, 69, 69, 72, 73, 74, 78, 80, 83, 88, 88, 88, 90, 92, 94, 94, 94, 94, 96, 100. Stem leaf: 33, 4299, 5355, 61378899, 72348, 8038888, 90244446, 10-0. Table 2.1 Stem and leaf graph. The stem plot shows that most scores fell in the 60s, 70s, 80s, and 90s. 8 out of the 31 scores, or approximately 26%, 831, were in the 90s or 100, a fairly high number of as. Try it 2.1. For the Park City basketball team, scores for the last 30 games were as follows: smallest to largest. 32, 32, 33, 34, 38, 40, 42, 42, 43, 44, 46, 47, 47, 48, 48, 48, 49, 50, 50, 51, 52, 52, 52, 53, 54, 56, 57, 57, 60, 61. Construct a stem plot for the data. The stem plot is a quick way to graph data and gives an exact picture of the data. You want to look for an overall pattern in any outliers. An outlier is an observation of data that does not fit the rest of the data. It is sometimes called an extreme value. When you graph an outlier, it will appear not to fit the pattern of the graph. Some outliers are due to mistakes, for example, writing down 50 instead of 500, while others may indicate that something unusual is happening. It takes some background information to explain outliers, so we will cover them in more detail later. Example 2.2. The data are the distances in kilometers from a home to local supermarkets. Create a stem plot using the data. 1.1, 1.5, 2.3, 2.5, 2.7, 3.2, 3.3, 3.3, 3.5, 3.8, 4, 4.2, 4.5, 4.5, 4.7, 4.8, 5.5, 5.6, 6.5, 6.7, 12.3. Problem: do the data seem to have any concentration of values? Note: the leaves are to the right of the decimal. Try at 2.2. The following data show the distances in miles from the homes of off-campus statistics students to the college. Create a stem plot using the data and identify any outliers. 0.5, 0.7, 1.1, 1.2, 1.2, 1.3, 1.3, 1.5, 1.5, 1.7, 1.7, 1.8, 1.9, 2, 2.2, 2.5, 2.6, 2.8, 2.8, 2.8, 3.5, 3.8, 4.4, 4.8, 4.9, 5.2, 5.5, 5.7, 5.8, 8. Example 2.3. Problem: a side-by-side stem and leaf plot allows a comparison of the two data sets in two columns. In a side-by-side stem and leaf plot, two sets of leaves share the same stem. The leaves are to the left and the right of the stems. Table 2.3 and Table 2.4 show the ages of presidents at their inauguration and at their death. Construct a side-by-side stem and leaf plot using this data. President age, President age, President A. Washington 57, Lincoln 52, Hoover 54. J. Adams 61A, Johnson 56F, Roosevelt 51. Jefferson 57, Grant 46, Truman 60. Madison 57, Hayes 54, Eisenhower 62. Monroe 58, Garfield 49, Kennedy 43. J.Q. Adams 57, Arthur 51 L, Johnson 55. Jackson 61, Cleveland 47, Nixon 56. Van Buren 54B, Harrison 55, Ford 61. W. H. Harrison 68, Cleveland 55, Carter 52. Tyler 51, McKinley 54, Reagan 69. Polk 49 T, Roosevelt 42 G. H. W. Bush 64. Taylor 64, Taft 51, Clinton 47. Fillmore 50, Wilson 56 G. W. Bush 54. Pierce 48, Harding 55, Obama 47. Buchanan 65, Coolidge 51. Table 2.3 Presidential ages at inauguration. President age, President age, President A. Washington 67, Lincoln 56, Hoover 90. J. Adams 90A, Johnson 66F, Roosevelt 63. Jefferson 83, Grant 63, Truman 88. Madison 85, Hayes 70, Eisenhower 78. Monroe 73, Garfield 49, Kennedy 46. J.Q. Adams 80, Arthur 56 L, Johnson 64. Jackson 78, Cleveland 71, Nixon 81. Van Buren 79 B, Harrison 67, Ford 93. W. H. Harrison 68, Cleveland 71, Reagan 93. Tyler 71, McKinley 58. Polk 53 T, Roosevelt 60. Taylor 65, Taft 72. Fillmore 74, Wilson 67. Pierce 64, Harding 57. Buchanan 77, Coolidge 60. Table 2.4 Presidential age at death. Try at 2.3. The table shows the number of wins and losses the Atlanta Hawks have had in 42 seasons. Create a side-by-side stem and leaf plot of these wins and losses. Losses win season, losses win season. 34-48, 141, 41, 22. 34-48, 239, 43, 23. 46-36, 3, 44, 38, 24. 46-36, 439, 43, 25. 36-46, 525, 57, 26. 47-35, 6, 40, 42, 27. 51-31, 7, 36, 46, 28. 5329 826 5629, 5131 9 32 50 30, 4141 10 19 31 31, 3646 11 54 28 32, 32 50 12 57 25 33, 5131 13 49 33 34, 40 42 14 47 35 35, 39 43 15 54 28 36, 42 40 16 69 13 37, 48 34 17 56 26 38, 32 50 18 52 30 39, 25 57 19 45 37 40, 32 50 20 35 47 41, 30 52 21 29 53 42. Table 2.6. Another type of graph that is useful for specific data values is a line graph. In the particular line graph shown in example 2.4, the x-axis, horizontal axis, consists of data values and the y-axis, vertical axis, consists of frequency points. The frequency points are connected using line segments. Example 2.4. In a survey, 40 parents were asked how many times per week a teenager must be reminded to do their chores. The results are shown in Table 2.7 and in Figure 2.2. Number of times teenager is reminded frequency: 2, 1 5, 2 8, 3 14, 4 7, 5 4. Table 2.7. A line graph showing the number of times a teenager needs to be reminded to do chores on the x-axis and frequency on the y-axis. Figure 2.2. Try 2.4. In a survey, 40 people were asked how many times per year they had their car in the shop for repairs. The results are shown in Table 2.8. Construct a line graph. Number of times in shop frequency: 7, 1 10, 2 14, 3 9. Table 2.8. Bar graphs consist of bars that are separated from each other. The bars can be rectangles or they can be rectangular boxes used in three-dimensional plots, and they can be vertical or horizontal. The bar graph shown in example 2.5 has age groups represented on the x-axis and proportions on the y-axis. Example 2.5. Problem: the percentage of US-based TikTok users by age is shown in Table 2.9. Construct a bar graph using this data. Age groups proportion percent of TikTok users: 10 19 32 5%, 20 29 29 5%, 30 39 16 4%, 40 49 13 9%, 50 plus 7 1%. Table 2.9. Try 2.5. The population in Park City is made up of children, working-age adults, and retirees. Table 2.1 shows the three age groups, the number of people in the town from each age group, and the proportion percent of people in each age group. Construct a bar graph showing the proportions. Age groups: number of people, proportion of population. Children 67, 0 59 19%. Working age adults 152, 198 43%. Retirees 131, 662 38%. Table 2.1. Example 2.6. Problem: the columns in Table 2.11 show the projected data for the year 2030 for the number and percentages of high school graduates by geographic region in the United States. Create a bar graph for this data with the geographic region, qualitative data, on the x-axis and the percentage of high school data, quantitative data, on the y-axis. Region: number of graduates, percentage of graduates. Northeast 517, 720 16, 1%. Midwest 695, 170 21, 6%. South 1 253, 540 39, 0%. West 749, 423, 3%. Table 2.11. Try 2.6. Park City is broken down into 6 voting districts. The table shows the percent of the total registered voter population that lives in each district, as well as the percent total of the entire population that lives in each district. Construct a bar graph that shows the registered voter population by district. District registered voter population, overall city population. 115 5%, 19 4%, 212 2%, 15 6%, 39 8%, 9 0%, 417 4%, 18 5%, 522 8%, 27%, 622 3%, 16 8%. Table 2.12. For most of the work you do in this book, you will use a histogram to display the data. One advantage of a histogram is that it can readily display large data sets. A rule of thumb is to use a histogram when the data set consists of 100 values or more. A histogram consists of contiguous adjoining boxes. It has both a horizontal axis and a vertical axis. The horizontal axis is labeled with what the data represents, for instance, distance from your home to school. The vertical axis is labeled either frequency or relative frequency or percent frequency or probability. The graph will have the same shape with either label. The histogram, like the stem plot, can give you the shape of the data, the center, and the spread of the data. The relative frequency is equal to the frequency for an observed value of the data divided by the total number of data values in the sample. Remember, frequency is defined as the number of times an answer occurs. If f equals frequency, n equals total number of data values or the sum of the individual frequencies, and rf equals relative frequency, then letter 1d445 letter 1d439 equals letter 1d453 letter 1d45b. For example, if 3 students in an English class of 40 students received from 90% to 100%, then f equals 3, n equals 40, and rf equals letter 1d453 letter 1d45b. Equals 340. Equals 0.075. 7.5% of the students received 90-100%. 90-100% are quantitative measures. To construct a histogram, first decide how many bars or intervals, also called classes, represent the data. Many histograms consist of 5 to 15 bars or classes for clarity. The number of bars needs to be chosen. Choose a starting point for the first interval to be less than the smallest data value. A convenient starting point is a lower value carried out to one more decimal place than the value with the most decimal places. For example, if the value with the most decimal places is 6.1 and this is the smallest value, a convenient starting point is 6.05. 6.10.05 equals 6.05. We say that 6.05 has more precision. If the value with the most decimal places is 2.23 and the lowest value is 1.5, a convenient starting point is 1.495. 1.5. 0.005 equals 1.495. The value with the most decimal places is 3.234 and the lowest value is 1. A convenient starting point is 0.9995. 0.0005 equals 0.9995. If all the data happen to be integers and the smallest value is 2, then a convenient starting point is 1.520. 0.5 equals 1.5. Also, when the starting point and other boundaries are carried to one additional decimal place, no data value will fall on a boundary. The next 2 examples go into detail about how to construct a histogram using continuous data and how to create a histogram using discrete data. Example 2.7. The following data are the heights in inches to the nearest half inch of 100 semi-professional soccer players. The heights are continuous data since height is measured. 60, 60.5, 61, 61, 61.5. 63.5, 63.5, 63.5. 64, 64, 64, 64, 64, 64, 64, 64.5, 64.5, 64.5, 64.5, 64.5, 64.5, 64.5, 64.5. 66, 66, 66, 66, 66, 66, 66, 66, 66, 66, 66.5, 66.5, 66.5, 66.5, 66.5, 66.5, 66.5, 66.5, 66.5, 66.5, 66.5, 67, 67, 67, 67, 67. 67, 67, 67, 67, 67, 67, 67, 67.5, 67.5, 67.5, 67.5, 67.5, 67.5, 67.5. 68, 68, 69, 69, 69, 69, 69, 69, 69, 69, 69, 69, 69.5, 69.5, 69.5, 69.5, 69.5. 70, 70, 70, 70, 70, 70, 70.5, 70.5, 70.5, 71, 71, 71. 72, 72, 72, 72.5, 72.5, 73, 73.5. 74. The smallest data value is 60. Since the data with the most decimal places has one decimal, for instance, 61.5, we want our starting point to have two decimal places. Since the numbers 0.5, 0.05, 0.005, etc. are convenient numbers, use 0.05 and subtract it from 60, the smallest value, for the convenient starting point. 60 0.05 equals 59.95, which is more precise than, say, 61.5 by one decimal place. The starting point is, then, 59.95. The largest value is 74, so 74 plus 0.05 equals 74.05 is the ending value. Next, calculate the width of each bar or class interval. To calculate this width, subtract the starting point from the ending value and divide by the number of bars. You must choose the number of bars you desire. Suppose you choose 8 bars. 74.05 minus 59.95 equals 14. 114. 1 divided by 8 equals 176. Note: we will round up to 2 and make each bar or class interval 2 units wide. Rounding up to 2 is one way to prevent a value from falling on a boundary. Rounding to the next number is often necessary even if it goes against the standard rules of rounding. For this example, using 1.76 as the width would also work. A guideline that is followed by some for the number of bars or class intervals is to take the square root of the number of data values and then round to the nearest whole number if necessary. For example, if there are 150 values of data, take the square root of 150 and round to 12 bars or intervals. The boundaries are 59.95. 59.95 plus 2 equals 61.95. 61.95 plus 2 equals 63.95. 63.95 plus 2 equals 65.95. 65.95 plus 2 equals 67.95. 67.95 plus 2 equals 69.95. 69.95 plus 2 equals 71.95. 71.95 plus 2 equals 73.95. 73.95 plus 2 equals 75.95. The height 60 through 61.5 inches are in the interval 59, 95, 61, 95. The heights that are 63.5 are in the interval 61, 95, 63, 95. The heights that are 64 through 64.5 are in the interval 63, 95, 65, 95. The heights 66 through 67.5 are in the interval 65, 95, 67, 95. The heights 68 through 69.5 are in the interval 67, 95, 69, 95. The heights 70 through 71 are in the interval 69, 95, 71, 95. The heights 72 through 73.5 are in the interval 71, 95, 73, 95. The height 74 is in the interval 73, 95, 75, 95. The following histogram displays the heights on the x-axis and relative frequency on the y-axis. Histogram consists of 8 bars with the y-axis in increments of 0.05 from 004 and the x-axis in intervals of 2 from 59.9 575 95. Figure 2.5. Try at 2.7. The following data are the shoe sizes of 50 students. The sizes are discrete data since shoe size is measured in whole and half units only. Construct a histogram and calculate the width of each bar or class interval. Suppose you choose 6 bars. 9, 9, 9.5, 9.5, 10, 10, 10, 10, 10, 10, 10.5, 10.5, 10.5, 10.5, 10.5, 10.5, 10.5, 10.5. 11, 11, 11, 11, 11, 11, 11, 11, 11, 11, 11, 11, 11, 11.5, 11.5, 11.5, 11.5, 11.5, 11.5, 11.5. 12, 12, 12, 12, 12, 12, 12, 12.5, 12.5, 12.5, 12.5, 14. Example 2.8. Create a histogram for the following data: the number of books bought by 50 part-time college students at ABC College. The number of books is discrete data since books are counted. 1 1 1 1 1 1 1 1 1 1 1 2 2 2 2 2 2 2 2 2 2 3 3 3 3 3 3 3 3 3 3 3 3 3 3 3 3 4 4 4 4 4 5 5 5 5 5 6 6 11 students buy 1 book, 10 students buy 2 books, 16 students buy 3 books, 6 students buy 4 books, 5 students buy 5 books, 2 students buy 6 books. Because the data are integers, subtract 0.5 from 1, the smallest data value, and add 0.5 to 6, the largest data value. Then the starting point is 0.5 and the ending value is 6.5. Problem. Next, calculate the width of each bar or class interval. If the data are discrete and there are not too many different values, a width that places the data values in the middle of the bar or class interval is the most convenient. Since the data consist of the numbers 1, 2, 3, 4, 5, 6, and the starting point is 0.5, a width of 1 places the 1 in the middle of the interval from 0.5 to 1.5, the 2 in the middle of the interval from 1.5 to 2.5, the 3 in the middle of the interval from 2.5 to 3.5, the 4 in the middle of the interval from 2, the 5 in the middle of the interval from 2, and the in the middle of the interval from. Calculate the number of bars as follows. 6 5 minus 0, 5 equals 66 divided by 1 equals 6. Where 1 is the width of a bar, therefore bars equals 6. The following histogram displays the number of books on the x-axis and the frequency on the y-axis. Histogram consists of 6 bars with the y-axis in increments of 2 from 0.16 and the x-axis in intervals of 1 from 0.565. Figure 2.6. Using the T83, 83 plus 84, 84 plus calculator. Go to Appendix G notes for the T83, 83 plus 84, 84 plus calculators. There are calculator instructions for entering data and for creating a customized histogram. Create the histogram for example 2.8. Press Y equals, press clear to delete any equations. Press Stat1 edit. If L1 has data in it, arrow up into the name L1, press clear and then arrow down. If necessary, do the same for L2. Into L1, enter 1, 2, 3, 4, 5, 6. Into L2, enter 11, 10, 16, 6, 5, 2. Press window, set xmin equals 0.5, xmax equals 6.5, xscl equals 6.5, 5/6, imin equals 1, imax equals 20, iscal equals 1, xres equals 1. Press second y equals, start by pressing 4, plots off enter. Press second y equals, press 1, plot 1, press enter, arrow down to type, arrow to the third picture histogram, press enter. Arrow down to xlist, enter L1, second 1, arrow down to freak, enter L2, second 2. Press graph. Use the trace key and the arrow keys to examine the histogram. Try a 2.8. The following data are the number of sports played by 50 student athletes. The number of sports is discrete data since sports are counted. 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 3 3 3 3 3 3 3 3 20 student athletes play 1 sport, 22 student athletes play 2 sports, 8 student athletes play 3 sports. Fill in the blanks for the following sentence. Since the data consist of the numbers 1, 2, 3, and the starting point is 0.5, a width of 1 places the 1 in the middle of the interval 0.52, the 2 in the middle of the interval from 2, and the 3 in the middle of the interval from 2. Example 2.9. Problem. Using this dataset, construct a histogram. Number of hours my classmates spent playing video games on weekends. 9 95 10 2 25 16 75 0. 19 5 22 5 7 5 15 12 75. 5 5 11 10 20 75 17 5. 23 21 9 24 23 75 18. 20 15 22 9 18 8 25. Table 2.13. Try a 2.9. The following data represent the number of employees at various restaurants in New York City. Using this data, create a histogram. 22, 35, 15, 26, 40, 28, 18, 20, 25, 34, 39, 42, 24, 22, 19, 27, 22, 34, 40, 20, 38, and 28. Use 10, 19 as the first interval. Collaborative exercise. Count the money, bills, and change in your pocket or purse. Your instructor will record the amounts. As a class, construct a histogram displaying the data. Discuss how many intervals you think is appropriate. You may want to experiment with the number of intervals. Frequency polygons. Frequency polygons are analogous to line graphs, and just as line graphs make continuous data visually easy to interpret, so too do frequency polygons. To construct a frequency polygon, first examine the data and decide on the number of intervals or class intervals to use on the x-axis and y-axis. After choosing the appropriate ranges, begin plotting the data points. After all the points are plotted, draw line segments to connect them. Example 2.1. A frequency polygon was constructed from the frequency table below. Frequency distribution for calculus final test scores. Lower bound, upper bound frequency, cumulative frequency. 49, 559, 555. 59, 569, 510, 15. 69, 579, 530, 45. 79, 589, 540, 85. 89, 599, 515, 100. Table 2.14. A frequency polygon was constructed from the frequency table below. Figure 2.8. The first label on the x-axis is 44.5. This represents an interval extending from 39.5 to 49.5. Since the lowest test score is 54.5, this interval is used only to allow the graph to touch the x-axis. The point labeled 54.5 represents the next interval, or the first real interval from the table, and contains 5 scores. This reasoning is followed for each of the remaining intervals, with the point 104.5 representing the interval from 99.5 to 109.5. Again, this interval contains no data and is only used so that the graph will touch the x-axis. Looking at the graph, we say that this distribution is skewed because one side of the graph does not mirror the other side. Try it 2.1. Construct a frequency polygon of U.S. presidents' ages at inauguration shown in Table 2.15. Age at inauguration frequency. 41, 546, 54. 46, 551, 511. 51, 556, 514. 56, 561, 59. 61, 566, 54. 66, 571, 52. Table 2.15. Frequency polygons are useful for comparing distributions. This is achieved by overlaying the frequency polygons drawn for different data sets. Example 2.11. We will construct an overlay frequency polygon comparing the scores from example 2.1 with the student's final numeric grade. Frequency distribution for calculus final test scores. Lower bound, upper bound frequency, cumulative frequency. 49, 559, 555. 59, 569, 510, 15. 69, 579, 530, 45. 79, 589, 540, 85. 89, 599, 515, 100. Table 2.16. Frequency distribution for calculus final grades. Lower bound, upper bound frequency, cumulative frequency. 49, 559, 510, 10. 59, 569, 510, 20. 69, 579, 530, 50. 79, 589, 540, 595. 89, 599, 55, 100. Table 2.17. This is an overlay frequency polygon that matches the supplied data. The x-axis shows the grades and the y-axis shows the frequency. Figure 2.9. Try it 2.11. We will construct an overlay frequency polygon comparing the scores from example 2.11 with the student's final test scores in algebra. Frequency distribution for algebra final test scores. Lower bound, upper bound frequency, cumulative frequency. 49, 559, 510, 10. 59, 569, 5515. 69, 579, 540, 55. 79, 589, 535, 90. 89, 599, 510, 100. Table 2.18. Constructing a time series graph. Suppose that we want to study the temperature range of a region for an entire month. Every day at noon we note the temperature and write this down in a log. A variety of statistical studies could be done with this data. We could find the mean or the median temperature for the month. We could construct a histogram displaying the number of days that temperatures reach a certain range of values. However, all of these methods ignore a portion of the data that we have collected. One feature of the data that we may want to consider is that of time. Since each date is paired with the temperature reading for the day, we don't have to think of the data as being random. We can instead use the times given to impose a chronological order on the data. A graph that recognizes this ordering and displays the changing temperature as the month progresses is called a time series graph. To construct a time series graph, we must look at both pieces of our paired data set. We start with a standard Cartesian coordinate system. The horizontal axis is used to plot the date or time increments, and the vertical axis is used to plot the values of the variable that we are measuring. By doing this, we make each point on the graph correspond to a date and a measured quantity. The points on the graph are typically connected by straight lines in the order in which they occur. Example 2.12. Problem. The following data shows the annual consumer price index each month for 10 years. Construct a time series graph for the annual consumer price index data only. Year Jan Feb Mar April May June July 181 7 183 184 2 183 8 183 5 183 7 183 9 2 185 2 186 2 187 4 188 0 189 1 189 7 189 4 3 190 7 191 8 193 3 194 6 194 4 194 5 195 4 4 198 3 198 7 199 8 201 5 202 5 202 9 203 5 5 202 416 203 499 205 352 206 686 207 949 208 352 208 299 6 211 0 80 211 693 213 528 214 823 216 632 218 815 219 964 7 211 143 212 193 212 709 213 240 213 856 215 693 215 351 8 216 687 216 741 217 631 218 009 218 178 217 965 218 011 9 220 223 221 309 223 467 224 906 225 964 225 722 225 922 10 226 665 227 663 229 392 230 085 229 815 229 478 229 104 Table 2.19 Year Og Sep Octnavdek Annual 1 184 6 185 2 185 0 184 5 184 3 184 0 2 189 5 189 9 190 9 191 0 190 3 188 9 3 196 4 198 8 199 2 197 6 196 8 195 3 4 203 9 202 9 201 8 201 5 201 8 201 6 5 207 917 208 490 208, 936 210, 177 210, 036 207, 342. 6 219 086 218, 783 216, 573 212, 425 210, 228 215, 303. 7 215, 834 215, 969 216, 177 216, 330 215, 949 214, 537. 8 218, 312 218, 439 218, 711 218, 803 219, 179 218, 056. 9 226, 545 226, 889 226, 421 226, 230 225, 672 224, 939. 10 230, 379 231, 407 231, 317 230, 221 229, 601 229, 594. Table 2.2. Try a 2.12. The following table is a portion of a data set from www.worldbank.org. Use the table to construct a time series graph for CO2 emissions for the United States. CO2 emissions. Year: Ukraine, United Kingdom, United States. 1 352, 259, 540, 645, 681, 664. 2 343, 121, 540, 409, 5 790, 761. 3 339, 0 29, 541, 995, 826, 394. 4 327, 797, 542, 0 45, 5 737, 615. 5 328, 357, 528, 631, 5 828, 697. 6 323, 657, 522, 247, 5 656, 839. 7 272, 176, 474, 579, 5 299, 563. Table 2.21. Uses of a time series graph. Time series graphs are important tools in various applications of statistics. When recording values of the same variable over an extended period of time, sometimes it is difficult to discern any trend or pattern. However, once the same data points are displayed graphically, some features jump out. Time series graphs make trends easy to spot. How not to lie with statistics. It is important to remember that the very reason we develop a variety of methods to present data is to develop insights into the subject of what the observations represent. We want to get a sense of the data. Are the observations all very much alike, or are they spread across a wide range of values? Are they bunched at one end of the spectrum, or are they distributed evenly, and so on? We are trying to get a visual picture of the numerical data. Shortly, we will develop formal mathematical measures of the data, but our visual graphical presentation can say much. It can unfortunately also say much that is distracting, confusing, and simply wrong in terms of the impression the visual leaves. Many years ago, Darrell Huff wrote the book How to Lie with Statistics. It has been through 25+ printings and sold more than 1.5 million copies. His perspective was a harsh one and used many actual examples that were designed to mislead. He wanted to make people aware of such deception, but perhaps more importantly to educate so that others do not make the same errors inadvertently. Again, the goal is to enlighten with visuals that tell the story of the data. Pie charts have a number of common problems when used to convey the message of the data. Too many pieces of the pie overwhelm the reader. More than perhaps 5 or 6 categories ought to give an idea of the relative importance of each piece. This is after all the goal of a pie chart, what subset matters most relative to the others. If there are more components than this, then perhaps an alternative approach would be better, or perhaps some can be consolidated into an other category. Pie charts cannot show changes over time, although we see this attempted all too often. In federal, state, and city finance documents, pie charts are often presented to show the components of revenue available to the governing body for appropriation: income tax, sales tax, motor vehicle taxes, and so on. In and of itself, this is interesting information and can be nicely done with a pie chart. The error occurs when 2 years are set side by side. Because the total revenues change year to year, but the size of the pie is fixed, no real information is provided, and the relative size of each piece of the pie cannot be meaningfully compared. Histograms can be very helpful in understanding the data. Properly presented, they can be a quick visual way to present probabilities of different categories by the simple visual of comparing relative areas in each category. Here the error, purposeful or not, is to vary the width of the categories. This of course makes comparison to the other categories impossible. It does embellish the importance of the category with the expanded width because it has a greater area inappropriately, and thus visually says that that category has a higher probability of occurrence. Time series graphs perhaps are the most abused. A plot of some variable across time should never be presented on axes that change partway across the page either in the vertical or horizontal dimension. Perhaps the time frame is changed from years to months. Perhaps this is to save space or because monthly data was not available for early years. In either case, this confounds the presentation and destroys any value of the graph. If this is not done to purposefully confuse the reader, then it certainly is either lazy or sloppy work. Changing the units of measurement of the axis can smooth out a drop or accentuate one. If you want to show large changes, then measure the variable in small units, penny rather than thousands of dollars. And of course, to continue the fraud, be sure that the axis does not begin at 0, 0. If it begins at 0, 0, then it becomes apparent that the axis has been manipulated. Perhaps you have a client that is concerned with the volatility of the portfolio you manage. An easy way to present the data is to use long time periods on the time series graph. Use months or better, quarters rather than daily or weekly data. If that doesn't get the volatility down, then spread the time axis relative to the rate of return or portfolio valuation axis. If you want to show quick dramatic growth, then shrink the time axis. Any positive growth will show visually high growth rates. Do note that if the growth is negative, then this trick will show the portfolio is collapsing at a dramatic rate. Again, the goal of descriptive statistics is to convey meaningful visuals that tell the story of the data. Purposeful manipulation is fraud and unethical at the worst, but even at its best, making these type of errors will lead to confusion on the part of the analysis. The common measures of location are quartiles and percentiles. Quartiles divide an ordered data set into 4 equal parts. The 3 quartiles of a data set are labeled as Q1, Q2, and Q3. About 1/4 of the data falls on or below the first quartile Q1. About 1/2 of the data falls on or below the second quartile Q2. About 3/4 of the data falls on or below the first quartile Q3. In the same way, percentiles divide a data set into 100 equal parts. To calculate quartiles and percentiles, the data must be ordered from smallest to largest. Quartiles divide ordered data into quarters. Percentiles divide ordered data into hundreds. To score in the 90th percentile of an exam does not mean necessarily that you received 90% on a test. It means that 90% of test scores are the same or less than your score, and 10% of the test scores are the same or greater than your test score. Percentiles are useful for comparing values. For this reason, universities and colleges use percentiles extensively. One instance in which colleges and universities use percentiles is when SAT results are used to determine a minimum testing score that will be used as an acceptance factor. For example, suppose Duke accepts SAT scores at or above the 75th percentile. That translates into a score of at least 1220. Percentiles are mostly used with very large populations. Therefore, if you were to say that 90% of the test scores are less and not the same or less than your score, it would be acceptable because removing one particular data value is not significant. The median is a number that measures the center of the data. You can think of the median as the middle value, but it does not actually have to be one of the observed values. It is a number that separates ordered data into halves. Half the values are the same number or smaller than the median, and half the values are the same number or larger. For example, consider the following data. 1, 11.56, 7.24, 8, 9, 10, 6.8, 8.3, 2, 2, 10, 1. Ordered from smallest to largest. 1, 1, 2, 2, 4, 6, 6.8, 7.28, 8.3, 9, 10, 10, 11.5. Since there are 14 observations, the median is between the 7th value, 6.8, and the 8th value, 7.2. To find the median, add the two values together and divide by 2. 6, 8 plus 7, 2 equals 1414 divided by 2 equals 7. The median is 7. Half of the values are smaller than 7 and half of the values are larger than 7. Quartiles are numbers that separate the data into quarters. Quartiles may or may not be part of the data. To find the quartiles, first find the median or second quartile. The first quartile Q1 is the middle value of the lower half of the data, and the third quartile Q3 is the middle value or median of the upper half of the data. To get the idea, consider the same data set. 1, 1, 2, 2, 4, 6, 6.8, 7.28, 8.39, 10, 10, 11.5. The median or second quartile is 7. The lower half of the data are 1, 1, 2, 2, 4, 6, 6.8. The middle value of the lower half is 2. 1, 1, 2, 2, 4, 6, 6.8. The number 2, which is part of the data, is the first quartile. 1/4 of the entire sets of values are the same as or less than 2, and 3/4 of the values are more than 2. The upper half of the data is 7.2, 8, 8.3, 9, 10, 10, 11.5. The middle value of the upper half is 9. The third quartile Q3 is 9. 3/4, 75% of the ordered data set are less than 9. 1/4, 25% of the ordered data set are greater than 9. The third quartile is part of the data set in this example. The interquartile range is a number that indicates the spread of the middle half or the middle 50% of the data. It is the difference between the third quartile Q3 and the first quartile Q1. IQR equals Q3 Q1. The IQR can help to determine potential outliers. A value is suspected to be a potential outlier if it is less than 1.5 IQR below the first quartile or more than 1.5 IQR above the third quartile. Potential outliers always require further investigation. Note: a potential outlier is a data point that is significantly different from the other data points. These special data points may be errors or some kind of abnormality, or they may be a key to understanding the data. Example 2.13. Problem: for the following 13 real estate prices, calculate the IQR and determine if any prices are potential outliers. Prices are in dollars. 389,950, 230,500, 158,000, 479,000, 639,000, 114,950, 5,500,000, 387,000, 659,000, 529,000, 575,000, 488,800. 1,095,000. Try a 2.13. For the following 11 salaries, calculate the IQR and determine if any salaries are outliers. The salaries are in dollars. $33,000, $64,500, $28,000, $54,000, $72,000, $68,500, $69,000, $42,000, $54,000, $120,000, $40,500. Example 2.14. Problem: test scores for a college statistics class held during the day are 99, 56, 78, 55.5, 32, 90, 80, 81, 56, 59, 45, 77, 84.5, 84, 70, 72, 68, 32, 79, 90. Test scores for a college statistics class held during the evening are 98, 78, 68, 83, 81, 89, 88, 76, 65, 45, 98, 90, 80, 84.5, 85, 79, 78, 98, 90, 79, 81, 25.5. For the two data sets, find the following. The interquartile range, compare the two interquartile ranges. Any outliers in either set. Try a 2.14. Find the interquartile range for the following two data sets and compare them. Test scores for Class A: 69, 96, 81, 79, 65, 76, 83, 99, 89, 67, 90, 77, 85, 98, 66, 91, 77, 69, 80, 94. Test scores for Class B: 90, 72, 80, 92, 90, 97, 92, 75, 79, 68, 70, 80, 99, 95, 78, 73, 71, 68, 95, 100. Example 2.15. 50 statistics students were asked how much sleep they get per school night, rounded to the nearest hour. The results were: amount of sleep per school night, HOURS, frequency, relative frequency, cumulative relative frequency. 420-040-04. 550-10-014. 670-14-028. 712-0-24-052. 814-0-28-080. 970-14-094. 1030-06100. Table 2.23. Find the 28th percentile. Notice the 0.28 in the cumulative relative frequency column. 28% of 50 data values is 14 values. There are 14 values less than the 28th percentile. They include the 2 4s, the 5 5s, and the 7 6s. The 28th percentile is between the last 6 and the first 7. The 28th percentile is 6.5. Find the median. Look again at the cumulative relative frequency column and find 0.52. The median is the 50th percentile or the second quartile. 50% of 50 is 25. There are 25 values less than the median. They include the 2 4s, the 5 5s, the 7 6s, and 11 of the 7s. The median or 50th percentile is between the 25th or 7 and 26th or 7 values. The median is 7. Find the third quartile. The third quartile is the same as the 75th percentile. You can eyeball this answer. If you look at the cumulative relative frequency column, you find 0.52 and 0.8. When you have all the 4s, 5s, 6s, and 7s, you have 52% of the data. When you include all the 8s, you have 80% of the data. The 75th percentile then must be an 8. Another way to look at the problem is to find 75% of 50, which is 37.5, and round up to 38. The third quartile, Q3, is the 38th value, which is an 8. You can check this answer by counting the values. There are 37 values below the third quartile and 12 values above. Try it 2.15. 40 bus drivers were asked how many hours they spend each day running their routes, rounded to the nearest hour. Find the 65th percentile. Amount of time spent on route hours, frequency, relative frequency, cumulative relative frequency. 212-0-30-0-30. 314-0-35-0-65. 410-0-25-0-90. 540-10-1-0-0. Table 2.24. A formula for finding the KTH percent. If you were to do a little research, you would find several formulas for calculating the KTH percentile. Here is one of them. K equals the KTH percentile. It may or may not be part of the data. I equals the index, ranking, or position of a data value. N equals the total number of data. Order the data from smallest to largest. Calculate letter 1D456 equals letter 1D458 100, letter 1D45B plus 1. If I is an integer, then the KTH percentile is the data value in the ith position in the ordered set of data. If I is not an integer, then round I up and round I down to the nearest integers. Average the two data values in these two positions in the ordered data set. This is easier to understand in an example. Example 2.16. Problem. Listed are 29 ages for Academy Award-winning Best Actors in order from smallest to largest. 18, 21, 22, 25, 26, 27, 29, 30, 31, 33, 36, 37, 41, 42, 47, 52, 55, 57, 58, 62, 64, 67, 69, 71, 72, 73, 74, 76, 77. Find the 70th percentile. Find the 83rd percentile. Try a 2.16. Listed are 29 ages for Academy Award-winning Best Actors in order from smallest to largest. 18, 21, 22, 25, 26, 27, 29, 30, 31, 33, 36, 37, 41, 42, 47, 52, 55, 57, 58, 62, 64, 67, 69, 71, 72, 73, 74, 76, 77. Calculate the 20th percentile and the 55th percentile. Note: you can calculate percentiles using calculators and computers. There are a variety of online calculators. Example 2.17. Problem. Using table 2.23. Find the 80th percentile. Find the 90th percentile. Find the first quartile. What is another name for the first quartile? Try at 2.17. Refer to the table 2.24. Find the third quartile. What is another name for the third quartile? Collaborative exercise. Your instructor or a member of the class will ask everyone in class how many sweaters they own. Answer the following questions. How many students were surveyed? What kind of sampling did you do? Construct two different histograms. For each, starting value equals ending value equals. Find the median, first quartile, and third quartile. Construct a table of the data to find the following. The 10th percentile, the 70th percentile, the percent of students who own less than 4 sweaters. A formula for finding the percentile of a value in a data set. Order the data from smallest to largest. X equals the number of data values counting from the bottom of the data list up to, but not including the data value for which you want to find the percentile. Y equals the number of data values equal to the data value for which you want to find the percentile. N equals the total number of data. Calculate 100, then round to the nearest integer. Example 2.18. Problem. Listed are 29 ages for Academy Award-winning Best Actors in order from smallest to largest. 18, 21, 22, 25, 26, 27, 29, 30, 31, 33, 36, 37, 41, 42, 47, 52, 55, 57, 58, 62, 64, 67, 69, 71, 72, 73, 74, 76, 77. Find the percentile for 58. Find the percentile for 25. Try a 2.18. Listed are 30 ages for Academy Award-winning Best Actors in order from smallest to largest. 18, 21, 22, 25, 26, 27, 29, 30, 31, 31, 33, 36, 37, 41, 42, 47, 52, 55, 57, 58, 62, 64, 67, 69, 71, 72, 73, 74, 76, 77. Find the percentiles for 47 and 31. Interpreting percentiles, quartiles, and median. A percentile indicates the relative standing of a data value when data are sorted into numerical order from smallest to largest. Percentages of data values are less than or equal to the PTH percentile. For example, 15% of data values are less than or equal to the 15th percentile. Low percentiles always correspond to lower data values. High percentiles always correspond to higher data values. A percentile may or may not correspond to a value judgment about whether it is good or bad. The interpretation of whether a certain percentile is good or bad depends on the context of the situation to which the data applies. In some situations, a low percentile would be considered good. In other contexts, a high percentile might be considered good. In many situations, there is no value judgment that applies. Understanding how to interpret percentiles properly is important not only when describing data, but also when calculating probabilities in later chapters of this text. Note: when writing the interpretation of a percentile in the context of the given data, the sentence should contain the following information. Information about the context of the situation being considered. The data value of the variable that represents the percentile. The percent of individuals or items with data values below the percentile. The percent of individuals or items with data values above the percentile. Example 2.19. Problem. On a timed math test, the first quartile for time it took to finish the exam was 35 minutes. Interpret the first quartile in the context of this situation. Try a 2.19. For the 100-meter dash, the third quartile for times for finishing the race was 11.5 seconds. Interpret the third quartile in the context of the situation. Example 2.2. Problem. On a 20-question math test, the 70th percentile for number of correct answers was 16. Interpret the 70th percentile in the context of this situation. Try a 2.2. On a 60-point written assignment, the 80th percentile for the number of points earned was 49. Interpret the 80th percentile in the context of this situation. Example 2.21. Problem. At a community college, it was found that the 30th percentile of credit units that students are enrolled for is 7 units. Interpret the 30th percentile in the context of this situation. Try a 2.21. During a season, the 40th percentile for points scored per player in a game is 8. Interpret the 40th percentile in the context of this situation. Example 2.22. Sharp Middle School is applying for a grant that will be used to add fitness equipment to the gym. The principal surveyed 15 anonymous students to determine how many minutes a day the students spend exercising. The results from the 15 anonymous students are shown. 0 minutes, 40 minutes, 60 minutes, 30 minutes, 60 minutes. 10 minutes, 45 minutes, 30 minutes, 300 minutes, 90 minutes. 30 minutes, 120 minutes, 60 minutes, 0 minutes, 20 minutes. Determine the following 5 values. Min equals 0. Q1 equals 20. Med equals 40. Q3 equals 60. Max equals 300. If you were the principal, would you be justified in purchasing new fitness equipment? Since 75% of the students exercise for 60 minutes or less daily, and since the IQR is 40 minutes, 60/20 equals 40, we know that half of the students surveyed exercise between 20 minutes and 60 minutes daily. This seems a reasonable amount of time spent exercising, so the principal would be justified in purchasing the new equipment. However, the principal needs to be careful. The value 300 appears to be a potential outlier. Q3 plus 1, 5 ICR equals 60 plus 1, 5, 40 equals 120. The value 300 is greater than 120, so it is a potential outlier. If we delete it and calculate the 5 values, we get the following values. Min equals 0. Q1 equals 20. Q3 equals 60. Max equals 120. We still have 75% of the students exercising for 60 minutes or less daily and half of the students exercising between 20 and 60 minutes a day. However, 15 students is a small sample, and the principal should survey more students to be sure of his survey results. Try at 2.22. A college statistics instructor is investigating the amount of time students spend working on a final project in the course. The instructor would like students to spend approximately 3 to 4 hours as the typical amount of time to be spent on the project. The instructor collects data from a random sample of 10 students for the number of hours spent working on the final project. The results obtained are as follows. 2 hours, 3 hours, 5 hours, 3 hours, 4 hours. 4 hours, 3 hours, 11 hours, 3 hours, 2 hours. Determine the following 5 values: min, Q1, med, Q3, max. Should the instructor modify the final project or leave as is? Box plots, also called box and whisker plots or box whisker plots, give a good graphical image of the concentration of the data. They also show how far the extreme values are from most of the data. A box plot is constructed from 5 values: the minimum value, the first quartile, the median, the third quartile, and the maximum value. We use these values to compare how close other data values are to them. To construct a box plot, use a horizontal or vertical number line in a rectangular box. The smallest and largest data values label the endpoints of the axis. The first quartile marks one end of the box and the third quartile marks the other end of the box. Approximately the middle 50% of the data fall inside the box. The whiskers extend from the ends of the box to the smallest and largest data values. The median or second quartile can be between the first and third quartiles, or it can be one or the other, or both. The box plot gives a good, quick picture of the data. Note: you may encounter box and whisker plots that have dots marking outlier values. In those cases, the whiskers are not extending to the minimum and maximum values. Consider again this dataset. 1, 1, 2, 2, 4, 6, 6.8, 7.28, 8.39, 10, 10, 11.5. The first quartile is 2, the median is 7, and the third quartile is 9. The smallest value is 1, and the largest value is 11.5. The following image shows the constructed box plot. Note: see the calculator instructions on the T website or in the appendix. Horizontal box plot's first whisker extends from the smallest value, 1, to the first quartile 2. The box begins at the first quartile and extends to the third quartile 9. A vertical dashed line is drawn at the median 7, and the second whisker extends from the third quartile to the largest value of 11.5. Figure 2.11. The two whiskers extend from the first quartile to the smallest value and from the third quartile to the largest value. The median is shown with a dashed line. Note: it is important to start a box plot with a scaled number line, otherwise the box plot may not be useful. Example 2.23. The following data are the heights of 40 students in a statistics class. 59, 60, 61, 62, 62, 63, 63, 64, 64, 64, 65, 65, 65, 65, 65, 65, 65, 65, 65, 66, 66, 67, 67, 68, 68, 69, 70, 70, 70, 70, 70, 71, 71, 72, 72, 73, 74, 74, 75, 77. Construct a box plot with the following properties. The calculator instructions for the minimum and maximum values as well as the quartiles follow the example. Minimum value equals 59. Maximum value equals 77. Q1 first quartile equals 64.5. Q2 second quartile or median equals 66. Q3 third quartile equals 70. Horizontal box plot with first whisker extending from smallest value 59 to Q1, 64.5, box beginning from Q1 to Q3, 70, median dashed line at Q2, 66, and second whisker extending from Q3 to largest value, 77. Figure 2.12. Each quarter has approximately 25% of the data. The spreads of the four quarters are 64.5, 59 equals 5.5 first quarter, 66, 64.5 equals 1.5 second quarter, 70, 66 equals 4 third quarter, and 77, 70 equals 7 fourth quarter. So the second quarter has the smallest spread and the fourth quarter has the largest spread. Range equals maximum value, the minimum value equals 77, 59 equals 18. Interquartile range, IQR equals Q3, Q1 equals 70, 64.5 equals 5.5. The interval 59-65 has more than 25% of the data, so it has more data in it than the interval 66 through 70, which has 25% of the data. The middle 50% middle half of the data has a range of 5.5 inches. Using the T83, 83 plus, 84, 84 plus calculator. To find the minimum, maximum in quartiles. Enter data into the list editor Pres Stat1, Edits. If you need to clear the list, arrow up to the name L1, press clear, and then arrow down. Put the data values into the list L1. Press Stat and arrow to CALC, press 1 var stats, enter L1. Press Enter. Use the down and up arrow keys to scroll. Smallest value equals 59. Largest value equals 77. Q1 first quartile equals 64.5. Q2 second quartile or median equals 66. Q3 third quartile equals 70. To construct the box plot, press 4 plots off, press Enter. Arrow down and then use the right arrow key to go to the fifth picture, which is the box plot. Press Enter. Arrow down to XList, press second one for L1. Arrow down to Freak, press Alpha, press 1. Press Zoom, press 9 Zoom Stat. Press Trace and use the arrow keys to examine the box plot. Try a 2.23. The following data are the number of pages in 40 books on a shelf. Construct a box plot using a graphing calculator and state the interquartile range. 136, 140, 178, 190, 205, 215, 217, 218, 232, 234, 240, 255, 207, 275, 290, 301, 303, 315, 317, 318, 326, 333, 343, 349, 360, 369, 377, 388, 391, 392, 398, 400, 402, 405, 408, 422, 429, 450, 475, 512. For some sets of data, some of the largest value, smallest value, first quartile, median, and third quartile may be the same. For instance, you might have a data set in which the median and the third quartile are the same. In this case, the diagram would not have a dotted line inside the box displaying the median. The right side of the box would display both the third quartile and the median. For example, if the smallest value and the first quartile were both 1, the median and the third quartile were both 5, and the largest value was 7, the box plot would look like. Horizontal box plot box begins at the smallest value and Q1, 1, until the Q3 and median, 5, no median line is designated, and has its lone whisker extending from the Q3 to the largest value, 7. Figure 2.13. In this case, at least 25% of the values are equal to 1. 25% of the values are between 1 and 5, inclusive. At least 25% of the values are equal to 5. The top 25% of the values fall between 5 and 7, inclusive. Example 2.24. Test scores for a college statistics class held during the day are 99, 56, 78, 55.5, 32, 90, 80, 81, 56, 59, 45, 77, 84.5, 84, 70, 72, 68, 32, 79, 90. Test scores for a college statistics class held during the evening are 98, 78, 68, 83, 81, 89, 88, 76, 65, 45, 98, 90, 80, 84.5, 85, 79, 78, 98, 90, 79, 81, 25.5. Problem: find the smallest and largest values, the median, and the first and third quartile for the day class. Find the smallest and largest values, the median, and the first and third quartile for the night class. For each data set, what percentage of the data is between the smallest value and the first quartile and the median and the third quartile and the largest value? What percentage of the data is between the first quartile and the largest value? Create a box plot for each set of data. Use one number line for both box plots. Which box plot has the widest spread for the middle 50% of the data between the first and third quartiles? What does this mean for that set of data in comparison to the other set of data? Try a 2.24. The following data set shows the heights in inches for the boys in a class of 40 students. 66, 66, 67, 67, 68, 68, 68, 68, 68, 69, 69, 69, 70, 71, 72, 72, 72, 73, 73, 74. The following data set shows the heights in inches for the girls in a class of 40 students. 61, 61, 62, 62, 63, 63, 63, 65, 65, 65, 66, 66, 66, 67, 68, 68, 68, 69, 69, 69. Construct a box plot using a graphing calculator for each data set and state which box plot has the wider spread for the middle 50% of the data. Example 2.25. Graph a box and whisker plot for the data values shown. 10, 10, 10, 15, 35, 75, 90, 95, 100, 175, 420, 490, 515, 515, 790. The 5 numbers used to create a box and whisker plot are min 10, Q1 15, mid 95, Q3 490, max 790. The following graph shows the box and whisker plot. Horizontal box plot with first whisker extending from smallest value 10 to Q1 15, box beginning from Q1 to Q3 490, median dashed line at Q2 95, and second whisker extending from Q3 to largest value 790. Figure 2.15. Try a 2.25. Follow the steps you used to graph a box and whisker plot for the data values shown. 0, 5, 5, 15, 30, 30, 45, 50, 50, 60, 75, 110, 140, 240, 330. The center of a data set is also a way of describing location. The two most widely used measures of the center of the data are the mean average and the median. To calculate the mean weight of 50 people, add the 50 weights together and divide by 50. To find the median weight of the 50 people, order the data and find the number that splits the data into 2 equal parts. The median is generally a better measure of the center when there are extreme values or outliers because it is not affected by the precise numerical values of the outliers. The mean is the most common measure of the center. Note: the words mean and average are often used interchangeably. The substitution of one word for the other is common practice. The technical term is arithmetic mean, and average is technically a center location. However, in practice among non-statisticians, average is commonly accepted for arithmetic mean. When each value in the data set is not unique, the mean can be calculated by multiplying each distinct value by its frequency and then dividing the sum by the total number of data values. The letter used to represent the sample mean is an X with a bar over it, pronounced X bar, X. The Greek letter mu, pronounced mu, represents the population mean. One of the requirements for the sample mean to be a good estimate of the population mean is for the sample taken to be truly random. To see that both ways of calculating the mean are the same, consider the sample. 1 1 1 2 2 3 4 4 4 4. Letter 1 D465 equals 1 plus 1 plus 1 plus 2 plus 2 plus 3 plus 4 plus 4 plus 4 plus 4 plus 411 equals 2, 7. Letter 1 D465 equals 3 1 plus 2 2 plus 1 3 plus 5 411 equals 2, 7. In the second calculation, the frequencies are 3, 2, 1, and 5. You can quickly find the location of the median by using the expression n plus 12. The letter n is the total number of data values in the sample. If n is an odd number, the median is the middle value of the ordered data, ordered smallest to largest. If n is an even number, the median is equal to the two middle values added together and divided by 2 after the data has been ordered. For example, if the total number of data values is 97, then n plus 12 equals 97 plus 12 equals 49. The median is the 49th value in the ordered data. If the total number of data values is 100, then n plus 12 equals 100 plus 12 equals 50.5. The median occurs midway between the 50th and 51st values. The location of the median and the value of the median are not the same. The uppercase letter M is often used to represent the median. The next example illustrates the location of the median and the value of the median. Example 2.26. Problem. A hospital administrator keeps track of the ages in years of patients visiting the emergency room over a 1-week period. Data are sorted from smallest to largest. 3, 4, 8, 8, 10, 11, 12, 13, 14, 15, 15, 16, 16, 17, 17, 18, 21, 22, 22, 24, 24, 25, 26, 26, 27, 27, 29, 29, 31, 32, 33, 33, 34, 34, 35, 37, 40, 44, 44, 47. Calculate the mean and the median. Using the T83, 83 plus 84, 84 plus calculator. To find the mean and the median. Clear list L1, pre-stat 4 CLR list. Enter second one for list L1, press enter. Enter data into the list editor, press stat 1 edit. Put the data values into list L1. Press stat and arrow to CALC, press 1 var stats, press second one for L1 and then enter. Press the down and up arrow keys to scroll. Letter 1 D465 equals 23.6, M equals 24. Try at 2.26. The following data show the number of months patients typically wait on a transplant list before getting surgery. The data are ordered from smallest to largest. Calculate the mean and median. 3, 4, 5, 7, 7, 7, 7, 8, 8, 9, 9, 10, 10, 10, 10, 10, 11, 12, 12, 13, 14, 14, 15, 15, 17, 17, 18, 19, 19, 19, 21, 21, 22, 22, 23, 24, 24, 24, 24. Example 2.27. Problem. Suppose that in a small town of 50 people, one person earns $5 million per year and the other 49 each earn $30,000. Which is the better measure of the center, the mean or the median? Try at 2.27. In a sample of 60 households, one house is worth $2,500,000. $20 9 houses are worth $280,000 and all the others are worth $315,000. Which is the better measure of the center, the mean or the median? Another measure of the center is the mode. The mode is the most frequent value. There can be more than one mode in a data set as long as those values have the same frequency and that frequency is the highest. A data set with 2 modes is called bimodal. Example 2.28. Statistics exam scores for 20 students are as follows. 50, 53, 59, 59, 63, 63, 72, 72, 72, 72, 72, 76, 78, 81, 83, 84, 84, 84, 90, 93. Problem. Find the mode. Try a 2.28. The number of books checked out from the library from 25 students are as follows. 000123344557777788889101011111212. Find the mode. Example 2.29. 5 real estate exam scores are 430, 430, 480, 480, 495. The data set is bimodal because the scores 430 and 480 each occur twice. When is the mode the best measure of the center? Consider a weight loss program that advertises a mean weight loss of 6 pounds the first week of the program. The mode might indicate that most people lose 2 pounds the first week, making the program less appealing. Note: the mode can be calculated for qualitative data as well as for quantitative data. For example, if the data set is red, 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 green, green, yellow, purple, black, blue, the mode is red. Statistical software will easily calculate the mean, the median, and the mode. Some graphing calculators can also make these calculations. In the real world, people make these calculations using software. Try a 2.29. 5 credit scores are 680, 680, 700, 720, 720. The data set is bimodal because the scores 680 and 720 each occur twice. Consider the annual earnings of workers at a factory. The mode is $25,000 and occurs 150 times out of 301. The median is $50,000 and the mean is $47,500. What would be the best measure of the center? The law of large numbers and the mean. The law of large numbers says that if you take samples of larger and larger size from any population, then the mean letter 1d465 of the sample is very likely to get closer and closer to micro. This is discussed in more detail later in the text. Sampling distributions and statistic of a sampling distribution. You can think of a sampling distribution as a relative frequency distribution with a great many samples. See sampling and data for a review of relative frequency. Suppose 30 randomly selected students were asked the number of movies they watched the previous week. The results are in the relative frequency table shown below. Hash of movies relative frequency. 530. 1 1530. 2 630. 3 330. 4 130. Table 2.25. If you let the number of samples get very large, say 300 million or more, the relative frequency table becomes a relative frequency distribution. A statistic is a number calculated from a sample. Statistic examples include the mean, the median, and the mode, as well as others. The sample mean letter 1d465 is an example of a statistic which estimates the population mean mu. Calculating the mean of grouped frequency tables. When only grouped data is available, you do not know the individual data values. We only know intervals and interval frequencies. Therefore, you cannot compute an exact mean for the data set. What we must do is estimate the actual mean by calculating the mean of a frequency table. A frequency table is a data representation in which grouped data is displayed along with the corresponding frequencies. To calculate the mean from a grouped frequency table, we can apply the basic definition of mean. Mean equals data sum number of data values. We simply need to modify the definition to fit within the restrictions of a frequency table. Since we do not know the individual data values, we can instead find the midpoint of each interval. The midpoint is lower boundary plus upper boundary 2. We can now modify the mean definition to be mean of frequency table equals sum letter 1d453 letter 1d45a sum sign letter 1d453. Where f equals the frequency of the interval and m equals the midpoint of the interval. Example 2.3. Problem. A frequency table displaying Professor Blount's last statistic test is shown. Find the best estimate of the class mean. Grade interval number of students. 50 56 51. 56 562 50. 62 568 54. 68 574 54. 74 580 52. 85 86 53. 86 592 54. 92 598 51. Table 2.26. Try a 2.3. A researcher conducted a study on the effect that playing video games has on memory recall. As part of the study, they compiled the following data. Hours teenagers spend on video games. Number of teenagers: 0353, 35757, 7511 512, 11 515 57, 15 519 59. Table 2.28. What is the best estimate for the mean number of hours spent playing video games? Consider the following data set: 4 5 6 6 6 7 7 7 7 7 7 8 8 8 9 10. This data set can be represented by following histogram. Each interval has width 1 and each value is located in the middle of an interval. This histogram matches the supplied data. It consists of 7 adjacent bars with the x-axis split into intervals of 1 from 4 to 10. The highs of the bars peak in the middle and taper symmetrically to the right and left. Figure 2.16. The histogram shown in Figure 2.16 displays a symmetrical distribution of data. A distribution is symmetrical if a vertical line can be drawn at some point in the histogram such that the shape to the left and the right of the vertical line are mirror images of each other. The mean, the median, and the mode are each 7 for these data. In a perfectly symmetrical distribution, the mean and the median are the same. This example has one mode, unimodal, and the mode is the same as the mean and median. In a symmetrical distribution that has 2 modes, bimodal, the 2 modes would be different from the mean and median. The histogram for the data 4 5 6 6 6 7 7 7 7 8 shown in Figure 2.17 is not symmetrical. The right-hand side seems chopped off compared to the left side. A distribution of this type is called skewed to the left because it is pulled out to the left. This histogram matches the supplied data. It consists of 5 adjacent bars with the x-axis split into intervals of 1 from 4 to 8. The peak is to the right and the heights of the bars taper down to the left. Figure 2.17. The mean is 6.3, the median is 6.5, and the mode is 7. Notice that the mean is less than the median and they are both less than the mode. The mean and the median both reflect the skewing, but the mean reflects it more so. The histogram for the data 6 7 7 7 7 8 8 8 9 10 Figure 2.18 is also not symmetrical. It is skewed to the right. This histogram matches the supplied data. It consists of 5 adjacent bars with the x-axis split into intervals of 1 from 6 to 10. The peak is to the left and the heights of the bars taper down to the right. Figure 2.18. The mean is 7.7, the median is 7.5, and the mode is 7. Of the 3 statistics, the mean is the largest, while the mode is the smallest. Again, the mean reflects the skewing the most. The mean is affected by outliers that do not influence the median. Therefore, when the distribution of data is skewed to the left, the mean is often less than the median. When the distribution is skewed to the right, the mean is often greater than the median. In symmetric distributions, we expect the mean and median to be approximately equal in value. This is an important connection between the shape of the distribution and the relationship of the mean and median. It is not, however, true for every data set. The most common exceptions occur in sets of discrete data. Skewness and symmetry become important when we discuss probability distributions in later chapters. Example 2.31. Problem. Statistics are used to compare and sometimes identify authors. The following list shows a simple random sample that compares the letter counts for 3 authors. Terry 7933341322. Davis 3334143231. Maris 23444666683. Make a dot plot for the 3 authors and compare the shapes. Calculate the mean for each. Calculate the median for each. Describe any pattern you notice between the shape and the measures of center. Try a 2.31. Discuss the mean, median, and mode for each of the following problems. Is there a pattern between the shape and measure of the center? This dot plot matches the supplied data. The plot uses a number line from 0 to 14. It shows 2 x's over 0, 4 x's over 1, 3 x's over 2, 1 x over 3, 2 x's over the number 4, 5, 6, and 9, and 1 x each over 10 and 14. There are no x's over the numbers 7, 8, 11, 12, and 13. Figure 2.22. The ages former U.S. presidents died. 469. 5367778. 6003344567778, 70112347889, 801358, 90033. Key 80 means 80. Table 2.29. Say, this is a histogram titled Hours Spent Playing Video Games on Weekends. The x-axis shows the number of hours spent playing video games with bars showing values at intervals of 5. The y-axis shows the number of students. The first bar for 0, 4.99 hours has a height of 2. The second bar from 5, 9.99 has a height of 3. The third bar from 10, 14.99 has a height of 4. The fourth bar from 15, 19.99 has a height of 7. The fifth bar from 20, 24.99 has a height of 9. Figure 2.23. An important characteristic of any set of data is the variation in the data. In some data sets, the data values are concentrated closely near the mean. In other data sets, the data values are more widely spread out from the mean. The most common measure of variation, or spread, is the standard deviation. The standard deviation is a number that measures how far data values are from their mean. The standard deviation provides a numerical measure of the overall amount of variation in a data set and can be used to determine whether a particular data value is close to or far from the mean. The standard deviation provides a measure of the overall variation in a data set. The standard deviation is always positive or 0. The standard deviation is small when the data are all concentrated close to the mean, exhibiting little variation or spread. The standard deviation is larger when the data values are more spread out from the mean, exhibiting more variation. Suppose that we are studying the amount of time customers wait in line at the checkout at Supermarket A and Supermarket B. The average wait time at both supermarkets is 5 minutes. At Supermarket A, the standard deviation for the wait time is 2 minutes. At Supermarket B, the standard deviation for the wait time is 4 minutes. Because Supermarket B has a higher standard deviation, we know that there is more variation in the wait times at Supermarket B overall. Wait times at Supermarket B are more spread out from the average. Wait times at Supermarket A are more concentrated near the average. The standard deviation can be used to determine whether a data value is close to or far from the mean. Suppose that Rosa and Ben both shop at Supermarket A. Rosa waits at the checkout counter for 7 minutes and Ben waits for 1 minute. At Supermarket A, the mean waiting time is 5 minutes and the standard deviation is 2 minutes. The standard deviation can be used to determine whether a data value is close to or far from the mean. Rosa waits for 7 minutes. 7 is 2 minutes longer than the average of 5. 2 minutes is equal to 1 standard deviation. Rosa's wait time of 7 minutes is 2 minutes longer than the average of 5 minutes. Rosa's wait time of 7 minutes is 1 standard deviation above the average of 5 minutes. Ben waits for 1 minute. 1 is 4 minutes less than the average of 5. 4 minutes is equal to 2 standard deviations. Ben's wait time of 1 minute is 4 minutes less than the average of 5 minutes. Ben's wait time of 1 minute is 2 standard deviations below the average of 5 minutes. A data value that is 2 standard deviations from the average is just on the borderline for what many statisticians would consider to be far from the average. Considering data to be far from the mean, if it is more than 2 standard deviations away, is more of an approximate rule of thumb than a rigid rule. In general, the shape of the distribution of the data affects how much of the data is further away than 2 standard deviations. You will learn more about this in later chapters. The number line may help you understand standard deviation. If we were to put 5 and 7 on a number line, 7 is to the right of 5. We say then that 7 is 1 standard deviation to the right of 5 because 5 plus 1, 2 equals 7. If 1 were also part of the data set, then 1 is 2 standard deviations to the left of 5 because 5 plus 2, 2 equals 1. This shows a number line in intervals of 1 from 0 to 7. Figure 2.24. In general, a value equals mean plus of stdev, standard deviation, where of stdev is equals the number of standard deviations. Of stdev does not need to be an integer. 1 is 2 standard deviations less than the mean of 5 because 1 equals 5 plus 2, 2. The equation value equals mean plus of stdev, standard deviation, can be expressed for a sample and for a population. Sample x equals letter 1 d465 plus letter 1 d45c letter 1 d453 letter 1 d446 letter 1 d447 letter 1 d437 letter 1 d438 letter 1 d449 letter 1 d460. Population letter 1 d465 equals letter 1 d707 plus hash letter 1 d45c letter 1 d453 letter 1 d446 letter 1 d447 letter 1 d437 letter 1 d438 letter 1 d449 letter 1 d70e. The lowercase letter s represents the sample standard deviation, and the Greek letter sigma, lowercase, represents the population standard deviation. The symbol letter 1 d465 is the sample mean, and the Greek symbol letter 1 d707 is the population mean. Calculating the standard deviation. If x is a number, then the difference x mean is called its deviation. In a data set, there are as many deviations as there are items in the data set. The deviations are used to calculate the standard deviation. If the numbers belong to a population, in symbols a deviation is x mu. For sample data, in symbols a deviation is x letter 1 d465. The procedure to calculate the standard deviation depends on whether the numbers are the entire population or are data from a sample. The calculations are similar, but not identical. Therefore, the symbol used to represent the standard deviation depends on whether it is calculated from a population or a sample. The lowercase letter s represents the sample standard deviation, and the Greek letter sigma, lowercase, represents the population standard deviation. If the sample has the same characteristics as the population, then s should be a good estimate of sigma. To calculate the standard deviation, we need to calculate the variance first. The variance is the average of the squares of the deviations, the x letter 1 d465 values for a sample, or the x mu values for a population. The symbol sigma 2 represents the population variance. The population standard deviation sigma is the square root of the population variance. The symbol s2 represents the sample variance. The sample standard deviation s is the square root of the sample variance. You can think of the standard deviation as a special average of the deviations. If the numbers come from a census of the entire population and not a sample, when we calculate the average of the squared deviations to find the variance, we divide by n the number of items in the population. If the data are from a sample rather than a population, when we calculate the average of the squared deviations, we divide by n1, one less than the number of items in the sample. Formulas for the sample standard deviation. Letter 1 d460 equals letter 1 d6f4, letter 1 d465 minus letter 1 d4652, letter 1 d45b minus 1 square. Or letter 1 d460 equals letter 1 d6f4, letter 1 d453, letter 1 d465 minus letter 1 d4652, letter 1 d45b minus 1 square. For the sample standard deviation, the denominator is n1, that is the sample size minus 1. Formulas for the population standard deviation. Letter 1 d70 equals letter 1 d6f4, letter 1 d465 minus letter 1 d7072, letter 1 d441 square. Or letter 1 d70 equals letter 1 d6f4, letter 1 d453, letter 1 d465, letter 1 d7072, letter 1 d441 square. For the population standard deviation, the denominator is n, the number of items in the population. In these formulas, f represents the frequency with which a value appears. For example, if a value appears once, f is 1. If a value appears 3 times in the data set or population, f is 3. Sampling variability of a statistic. The statistic of a sampling distribution was discussed in descriptive statistics. Measures of the center of the data. How much the statistic varies from one sample to another is known as the sampling variability of a statistic. You typically measure the sampling variability of a statistic by its standard error. The standard error of the mean is an example of a standard error. It is a special standard deviation and is known as the standard deviation of the sampling distribution of the mean. You will cover the standard error of the mean in the chapter The Central Limit Theorem, not now. The notation for the standard error of the mean is letter 1 d70, letter 1 d45b square root, where sigma is the standard deviation of the population and n is the size of the sample. Note: in practice, use a calculator or computer software to calculate the standard deviation. If you are using a T83, 83 plus, 84 plus calculator, you need to select the appropriate standard deviation sigmix or SX from the summary statistics. We will concentrate on using and interpreting the information that the standard deviation gives us. However, you should study the following step-by-step example to help you understand how the standard deviation measures variation from the mean. The calculator instructions appear at the end of this example. Example 2.32. In a fifth grade class, the teacher was interested in the average age and the sample standard deviation of the ages of the students. The following data are the ages for a sample of n equals 25th grade students. The ages are rounded to the nearest half year. 9, 9.5, 9.5, 10, 10, 10, 10, 10.5, 10.5, 10.5, 10.5, 11, 11, 11, 11, 11, 11, 11.5, 11.5, 11.5. Letter 1 D465 equals 9 plus 9, 5, 2 plus 10, 4 plus 10, 5, 4 plus 11, 6 plus 11, 5, 3, 20 equals 10, 525. The average age is 10.53 years, rounded to 2 places. The variance may be calculated by using a table. Then the standard deviation is calculated by taking the square root of the variance. We will explain the parts of the table after calculating S. Data freak deviations 2 freak deviations 2. XFX liter 1 D465. X liter 1 D465. 2FX liter 1 D465. 2. 919 10.525 equals 1 525. 1 525 2 equals 2 325,625 1 times 2.325625 equals 2.325625. 9 5295 10.525 equals 1 025 1 025 2 equals 1 050,625 2 times 1.050625 equals 2.10125. 10 410 10.525 equals 0 525 0 525 2 0 275,625 4 times 0.275625 equals 1.1025. 10 5 410 5 10.525 equals 0 025 0 025 2 equals 0 0.000625 4 times 0.000625 equals 0.0025. 11 6 11 10.525 equals 0 475 0 475 2 equals 0 225,625 6 times 0.225625 equals 1.35375. 11 5 3 11 5 10.525 equals 0 975 0 975 2 equals 0 950,625 3 times 0.950625 equals 2.851875. The total is 9.7375. Table 2.3. The sample variance S2 is equal to the sum of the last column 9.7375 divided by the total number of data values minus 1, 21. Letter 1 D4602 equals 9, 737,520 minus 1 equals 0, 5,125. The sample standard deviation S is equal to the square root of the sample variance. Letter 1 D460 equals 0, 5,125 square equals 0, 715,891. Which is rounded to 2 decimal places, S equals 0.72. Typically, you do the calculation for the standard deviation on your calculator or computer. The intermediate results are not rounded. This is done for accuracy. Problem. For the following problems, recall that value equals mean plus of stdev, standard deviation. Verify the mean and standard deviation or a calculator or computer. For a sample, x equals letter 1 D465 plus of stdev s. For a population, x equals mu plus of stdev sigma. For this example, use x equals letter 1 D465 plus of stdev s because the data is from a sample. Verify the mean and standard deviation on your calculator or computer. Find the value that is 1 standard deviation above the mean. Find letter 1 D465. Plus 1. Find the value that is 2 standard deviations below the mean. Find letter 1D465. 2. Find the values that are 1.5 standard deviations from below and above the mean. Try at 2.32. On a baseball team, the ages of each of the players are as follows: 21, 21, 22, 23, 24, 24, 25, 25, 28, 29, 29, 31, 32, 33, 33, 34, 35, 36, 36, 36, 36, 38, 38, 38. Use your calculator or computer to find the mean and standard deviation. Then find the value that is 2 standard deviations above the mean. Explanation of the standard deviation calculation shown in the table. The deviations show how spread out the data are about the mean. The data value 11.5 is farther from the mean than is the data value 11, which is indicated by the deviations 0.97 and 0.47. A positive deviation occurs when the data value is greater than the mean, whereas a negative deviation occurs when the data value is less than the mean. The deviation is 1.525 for the data value 9. If you add the deviations, the sum is always 0. For example 2.32, there are n equals 20 deviations. So you cannot simply add the deviations to get the spread of the data. By squaring the deviations, you make them positive numbers, and the sum will also be positive. The variance then is the average squared deviation. The variance is a squared measure and does not have the same units as the data. Taking the square root solves the problem. The standard deviation measures the spread in the same units as the data. Notice that instead of dividing by n equals 20, the calculation divided by n 1 equals 20, 1 equals 19 because the data is a sample. For the sample variance, we divide by the sample size minus 1 n 1. Why not divide by n? The answer has to do with the population variance. The sample variance is an estimate of the population variance. Based on the theoretical mathematics that lies behind these calculations, dividing by n 1 gives a better estimate of the population variance. Note: your concentration should be on what the standard deviation tells us about the data. The standard deviation is a number which measures how far the data are spread from the mean. Let a calculator or computer do the arithmetic. The standard deviation, S or sigma, is either 0 or larger than 0. Describing the data with reference to the spread is called variability. The variability in data depends upon the method by which the outcomes are obtained, for example, by measuring or by random sampling. When the standard deviation is 0, there is no spread, that is, all the data values are equal to each other. The standard deviation is small when the data are all concentrated close to the mean, and is larger when the data values show more variation from the mean. When the standard deviation is a lot larger than 0, the data values are very spread out about the mean. Outliers can make S or sigma very large. The standard deviation, when first presented, can seem unclear. By graphing your data, you can get a better feel for the deviations and the standard deviation. You will find that in symmetrical distributions, the standard deviation can be very helpful, but in skewed distributions, the standard deviation may not be much help. The reason is that the two sides of a skewed distribution have different spreads. In a skewed distribution, it is better to look at the first quartile, the median, the third quartile, the smallest value, and the largest value. Because numbers can be confusing, always graph your data. Display your data in a histogram or a box plot. Example 2.33. Problem: use the following data first exam scores from Professor Dean's spring pre-calculus class. 33, 42, 49, 49, 53, 55, 55, 61, 63, 67, 68, 68, 69, 69, 72, 73, 74, 78, 80, 83, 88, 88, 88, 90, 92, 94, 94, 94, 94, 96, 100. Create a chart containing the data, frequencies, and cumulative relative frequencies to 3 decimal places. Calculate the following to 1 decimal place using a T83 plus or T84 calculator. The sample mean, the sample standard deviation, the median, the first quartile, the third quartile, IQR. Construct a box plot and a histogram on the same set of axes. Make comments about the box plot, the histogram, and the chart. The long left whisker in the box plot is reflected in the left side of the histogram. The spread of the exam scores in the lower 50% is greater, 73.33 equals 40, than the spread in the upper 50%, 173 equals 27. The histogram, box plot, and chart all reflect this. There are a substantial number of A and B grades, 80s, 90s, and 100. The histogram clearly shows this. The box plot shows us that the middle 50% of the exam scores, IQR equals 29, are DS, CS, and BS. The box plot also shows us that the lower 25% of the exam scores are DS and FS. Try a 2.33. The following data show the different types of pet food stores in the area carry. 6, 6, 6, 7, 7, 7, 7, 8, 9, 9, 9, 9, 10, 10, 10, 10, 11, 11, 11, 11, 11, 12, 12, 12, 12, Calculate the sample mean and the sample standard deviation to one decimal place using a T83 plus or T84 calculator. Standard deviation of group frequency tables. Recall that for grouped data we do not know individual data values, so we cannot describe the typical value of the data with precision. In other words, we cannot find the exact mean, median, or mode. We can, however, determine the best estimate of the measures of center by finding the mean of the grouped data with the formula. Mean of frequency letter 1 D447, letter 1 D44, letter 1 D44F, letter 1 D459, letter 1 D452 equals sum letter 1 D453, letter 1 D45A, sum sign letter 1 D453, where letter 1 D453 equals interval frequencies and M equals interval midpoints. Just as we could not find the exact mean, neither can we find the exact standard deviation. Remember that standard deviation describes numerically the expected deviation a data value has from the mean. In simple English, the standard deviation allows us to compare how unusual individual data is compared to the mean. Example 2.34. Find the standard deviation for the data in Table 2.32. Class frequency F. Midpoint M. Letter 1 D453, letter 1 D45A. Letter 1 D465. Letter 1 D45A minus letter 1 D465. Letter 1 D45A minus letter 1 D4652. Letter 1 D453, letter 1 D45A minus letter 1 D4652. 021117 58-6 5843 2964 43 2964 3564 24/7 58-3 5812 8164 76 8984 6810 777 58-0 58-0 3364 3 364 911 710 77 58-2 42-5 8564 40 9948 12-14-0 13-0 58-5 42-29 3764 0 15-17-2 16-32 7 58-8 42-70 8964 141 7928 Sum letter 1 D7 2E 26 197 43 2964 Table 2.32. The values in the second, third, and fourth columns of Table 2.32 are used to calculate the mean of the grouped frequency table, the value in the fifth column. Letter 1 D465 equals letter 1 D6F4, letter 1 D453, letter 1 D45A, letter 1 D6F4, letter 1 D453 equals 19,726, approximately 758. After calculating letter 1 D465, find the difference letter 1 D45A minus letter 1 D465 for each midpoint M. Next, square each difference. In the final column, calculate the product of the frequency and the squared difference for each class. The table makes it easy to use the formula for calculating the standard deviation of a grouped frequency table. Letter 1 D460, letter 1 D465 equals letter 1 D6F4, letter 1 D453, letter 1 D45A minus letter 1 D465 to letter 1 D45B minus 1 square equals 43. 296,426 minus 1 square approximately 350. Although the formula is not complicated, these calculations are typically performed using technology. Try a 2.34. Find the standard deviation for the data from the previous example. Class frequency F. 021. 356. 6810. 911 7. 1214 0. 1517-2. Table 2.33. First, press the Stat key and select one edit. Image of a T-calculator screen. After pressing the Stat key, screen displays top menu choices Edit, CALC, Tests. Edit is selected. Below the top menu, option 1, Edit is selected. Figure 2.26. Input the midpoint values into L1 and the frequencies into L2. Image of a T-calculator screen. L1 list shows entries 1, 4, 7, 10, 13, 16. L2 list shows 1, 6, 10, 7, 0, 2. Figure 2.27. Select Stat CALC in 1 var stats. Image of a T-calculator screen. After pressing the Stat key, screen displays top menu choices Edit, CALC, Tests. CALC is selected. Below the top menu, option 1 var stats is selected. Figure 2.28. Select second then 1 then, second then 2, enter. Image of a T-calculator screen. At the top of the screen, the label shows 1 var stats. Below this label, the screen displays x bar equals 7.5769230077. Uppercase sigma x equals 197. Uppercase sigma x squared equals 1799. Sx equals 3.500549407. And lowercase sigma equals 3.4325711103. N equals 26. Figure 2.29. You will see displayed both a population standard deviation, sigmax, and the sample standard deviation, Sx. Comparing values from different datasets. The standard deviation is useful when comparing data values that come from different datasets. If the datasets have different means and standard deviations, then comparing the data values directly can be misleading. For each data value, calculate how many standard deviations away from its mean the value is. Use the formula value equals mean plus of stdev, standard deviation, solve for of stdevs. Value means standard deviation. Compare the results of this calculation. Of stdevs is often called a z-score. We can use the symbol z. In symbols, the formulas become example letter 1 d465 equals letter 1 d465 plus zs letter 1 d467 equals letter 1 d465 minus letter 1 d465 letter 1 d460. Population letter 1 d465 equals letter 1 d707 plus z sigma letter 1 d467 equals letter 1 d465 minus letter 1 d707 letter 1 d70e. Table 2.34. Example 2.35. Problem. Two students, John and Ali, from different high schools wanted to find out who had the highest GPA when compared to his school. Which student had the highest GPA when compared to his school? Student GPA school, mean GPA school, standard deviation. John 2853007. Ali 778010. Table 2.35. Try it 2.35. Two swimmers, Angie and Bate, from different teams wanted to find out who had the fastest time for the 50-meter freestyle when compared to her team. Which swimmer had the fastest time when compared to her team? Swimmer time, seconds, team mean time, team standard deviation. Angie 26-227-208. Beth 27-330-114. Table 2.36. The following lists give a few facts that provide a little more insight into what the standard deviation tells us about the distribution of the data. For any data set, no matter what the distribution of the data is, at least 75% of the data is within 2 standard deviations of the mean. At least 89% of the data is within 3 standard deviations of the mean. At least 95% of the data is within 4.5 standard deviations of the mean. This is known as Chebyshev's rule. For data having a distribution that is bell-shaped and symmetric, approximately 68% of the data is within 1 standard deviation of the mean. Approximately 95% of the data is within 2 standard deviations of the mean. More than 99% of the data is within 3 standard deviations of the mean. This is known as the empirical rule. It is important to note that this rule only applies when the shape of the distribution of the data is bell-shaped and symmetric. We will learn more about this when studying the normal or Gaussian probability distribution in later chapters. Stats Lab. Descriptive statistics. Class time. Names. Student learning outcomes. The student will construct a histogram and a box plot. The student will calculate univariate statistics. The student will examine the graphs to interpret what the data implies. Collect the data. Record the number of pairs of shoes you own. Randomly survey 30 classmates about the number of pairs of shoes they own. Record their values. Table 2.37 Survey results. Construct a histogram, make 5 to 6 intervals. Sketch the graph using a ruler and pencil and scale the axes. A blank graph template for use with this problem. Figure 2.3. Calculate the following values. Letter 1D465. Equals. S equals. Are the data discrete or continuous? How do you know? In complete sentences, describe the shape of the histogram. Are there any potential outliers? List the value S that could be outliers. Use a formula to check the end values to determine if they are potential outliers. Analyze the data. Determine the following values. Min equals. M equals. Max equals. Q1 equals. Q3 equals. IQR equals. Construct a box plot of data. What does the shape of the box plot imply about the concentration of data? Use complete sentences. Using the box plot, how can you determine if there are potential outliers? How does the standard deviation help you to determine concentration of the data and whether or not there are potential outliers? What does the IQR represent in this problem? Show your work to find the value that is 1.5 standard deviations. Above the mean. Below the mean.